this presentation, last year I did a presentation on why pixels flicker, and it ended up being a real adventure in examining exactly how pixel protocols are generated and how they degenerate over long pieces of wire and all of that sort of stuff. And if you didn't see that presentation at last year's VCS, I would encourage you to seek it out, particularly if you're a 12 volt user, because you're the guys that tend to have flickering pixels. And that presentation explains a lot about why it happens and what you can do about it. And so this year, when I was sort of putting together my list of presentations to do, I was kind of thinking about, well, what else would be interesting? What are the other questions or the things that I've always just taken for granted that it would actually be really interesting to deep dive into and understand? Is it actually true? Is that actually how it works? And what's the implications of it? And so we're going to do some deep dive into some things around the pixels themselves. Maybe ask some questions that you never thought to ask, or you'd always just assumed you knew, but at the end of the day, maybe you've never actually seen what happens in practice, and it'd be worthwhile doing. So that's what we're going to do for the next hour. So we're going to explore some of the less vanilla pixels. We're going to explore pixel performance and particularly brightness a lot, and what happens within a pixel, to see what that all looks like. Well, I want to start with pixel brightness. These days it seems like running pixels at full brightness is not the fashionable thing to do. But do people really understand exactly how brightness is being applied by both the software and the controllers and inside the pixel itself, and exactly how it all works? And what's the actual net effect of that brightness? Are you really seeing a linear response curve to the brightness settings in X-Lights? When you say to X-Lights, display that pixel at 50%, is it really 50% bright or isn't it? And how does that vary by color and things like that? And they were all the things that I wanted to try and understand. The results are a little bit mixed. There's some interesting things in it, but there are some other things in it which I wasn't entirely happy with, and we'll go through that and explain what that is. So how is brightness applied? It's important to understand how brightness is applied, because at the end of the day, X-Lights is really just setting a number per channel of a number between 0 and 255. And the way X-Lights applies brightness to that number is it effectively reduces it. So if you set the brightness to 50%, then instead of a value that goes from 0 to 255, you get a value that goes from 0 to 127. If you set it to 10%, then you're getting at a value that goes from 0 to 25 only. And none of those other values will ever be generated by X-Lights. And that has a pretty significant reduction in the number of theoretical colors. When you're running 3 channels at 0 to 255, that's 16 million possible color combinations. But once you've reduced it to 50%, you actually lose over 87% of the possible colors that your pixels can display as a result of that. It looks pretty scary. When you get to 10%, it's kind of like you lose all but 0.09% of the color range. So it has a pretty dramatic impact on the hypothetical color range. But is that significant? Does that really matter? The formula that X-Lights uses, and in fact your controller also uses, is it takes your old brightness, multiplies it by whatever percentage you've set it to, and divides it by 100. And once X-Lights has reduced the brightness, there's really nothing that's going to increase that brightness again. So that 0 to 255 reduced down to 0 to 127 is never going to be higher than that. That's the value that's going to end up being sent out to the individual pixels. So this is that same thing graphical. And so what you see is the red line here is the actual original value, and once you apply 50%, you can see how you get a linear reduction in the value that is sent out. So when you originally started with a 127 up here and you set it to 50%, you're getting a value that's closer to 64 that's actually going to be sent out to the pixel. But this is a linear curve. It responds purely linearly over that entire range. Now, when you do a fade, then once you've dimmed your pixels down and you do a fade, there's obviously less values that fade can go through. And so your fades will tend to get potentially a little bit more blocky, particularly slow fades. Fast fades are going to be jumpy at any rate, but when you're running a really slow fade over a number of frames, as you reduce the brightness, it's going to get a lot blockier because the color steps there's not as many color steps to go through as it fades away. And then when you apply brightness cumulatively, so if you set brightness in X lights and then you apply brightness in your show player or you apply brightness on your controller, that brightness is applied in a cumulative way. So if you set it to 50% in X lights, the 0 to 255 becomes 0 to 127. But then if you also set it to 50% in your controller, then that 0 to 127 becomes 0 to 63. So it accumulates. And that's also showable graphically here. So if your original value is the blue line, after it was applied in X lights, you got the red line, but then when you apply a further 50%, you can see that the lines are getting flatter and flatter and flatter, and therefore the number of values that can be sent out to the individual pixels become much more limited in their range. So I would generally recommend that you apply brightness in one location only rather than apply brightness in multiple areas. And as we discussed earlier in my earlier session, I would generally apply brightness on my controller rather than in X lights because it allows you to play with the brightness at show setup time, whereas if you do it in X lights, you have to go back and re-render all your sequences and send them back to your show player and all of that sort of hassle, which is really, really unnecessary. But just beware, when you're applying multiple brightnesses, you are really dramatically reducing the range of values that can be sent out for each channel as a result of doing that. But what about gamma? So some people have played with gamma, and you've heard people talk about using a gamma for Halloween of 2 so that you can get better oranges and better purples. Well, this is what a gamma curve is. So when you apply a gamma of 2.0, what it's doing is it's not changing the high value and it's not changing the low value, but all the values in the middle are being pulled down by a certain proportion. So your 255s are going to stay 255, your zeros are going to stay zeros, but your 128s are going to be substantially reduced. And in fact, they're reduced by a factor of 2, which is what the 2.0 kind of tells you. In the middle, it's reduced by 2, but as you get closer to the ends, the reduction is not as dramatic. And the formula for that is this value here, the old value divided by 255 raised to the power of the gamma multiplied by 255. Now, the interesting thing is you can actually apply this formula and work out the value. So if you don't want to apply a gamma of 2.0, but you'd like to get the orange that a gamma of 2.0 represents, then really, instead of using an orange of 255, 128, 0, just apply an orange of 255, 64 and 0, and that will be the same orange color that you would have got with a gamma 2.0. And a purple with a gamma of 2.0 becomes 64, 0 and 255. And you can calculate all of these values out rather than just blanket applying a gamma to your pixels. So pixels themselves, however, control the color using PWM, and you can actually see this. If you look at a pixel running here at low power, you can see that pixel there appears to be flickering. And the reason it's flickering is because the pixel is not actually lighting the LED up consistently. It's turning the LED on and off again at a frequency that is significantly faster than the frame rate of your of your sequence, whether it's 40 frames a second or 20 frames a second. And that's what's known as a PWM signal. And you can see it here on the oscilloscope. This high region here is when the pixel is being turned on, and then it's being turned off. It's a very, very noisy signal. And then it turns back on again, etc. Now, this is the one where I set the measurements on, and so you can see that the measurement time frame is 500 microseconds. So the cycle time for the actual turning on and off of the power within the pixel is 500 microseconds, which is half a millisecond. So within if you're running 40 frames a second, that means that the LED is actually turning on 50 times within each frame in order to generate the color. Okay, now this can vary by pixel type. So if you're using other pixels, they may run at a different frequency. The signal's also nowhere near as simple as I imagined. I thought that this was going to be a fairly straightforward square wave where the width of this wave got smaller and smaller as the power changed, but it's not. It's this noisy signal with lots and lots of harmonics. And if you run the data across many, many different signal levels, you can see here how it keeps getting shorter as I turn the brightness down. But it's never a clean signal. And in fact, it's even worse than that. As you get down to the low end here, it does some really, really, really strange things. So let's do this. Can we make this bigger? We can. So let's go to X-Lights and let's turn this thing up to 100%. So you can see here the oscilloscope is showing the pixel. Now this is set at 255 white, and you can see that the blue trace, that small piece here where it's high at the top, is actually what's driving the pixel. It never seems to drive it for the entire frame. I thought it would just turn on the color channel for the entire period of time, but it never seems to. It always seems to turn it off. And as I lower the brightness, you can see that this gap here will narrow at the top. So you can see how the top of it gets smaller and smaller, but the signal also starts to degenerate in a fairly significant way. And then once I get below about 30, the signal just goes really, really strange. It's not the clean type of PWM signal that I was expecting when I first set out to experiment this. So that's currently set at 37. I can only assume that this is the powering of the pixel up here, but it seems to be very insignificant in terms of a time period. Which makes you wonder how linear is going to be the response of these pixels if this is what you see on the scope when you trace the pixels out. I can see chat going off, but I'm not looking at chat, so someone will need to speak up if you want me to talk about it. The other thing that you notice here is that like I said, the PWM percentage at the bottom, it's just all over the place at the low end here. And take note of that, because that's actually going to come up a number of times in this presentation as we start to delve into some other things. So it's really hard to make sense of those low end waveforms. But at the high end, you can see that the time, and I've been putting measurements in on the time here. So here it was 172 microseconds. This one here dropped to 132, 94, 58, 52. And at this point here, and this was at about 30, I think, it had dropped down to only 4 microseconds was it actually high, which seems pretty small given that it was 30. I don't know how small it can really get. How does it translate into current draw? So shortly after I started work on this presentation, Stephen Nye actually came out with a video where he did a bunch of testing on some 12-volt pixels to see what the current draw of those pixels were and whether it was linear, and he produced some spreadsheets using various sample brightness levels to see what it looks like. And I'd encourage you to go and have a look at Steve's website or his YouTube channel. It's like Nye Family Lights if you want to search for it on YouTube. He's got a bunch of videos there around largely setup type activities and the like, but this was an interesting video that he did on power draw. And what he found in his results was that the current draw of the pixels was pretty linear. He saw a pretty linear performance there, but he only took select samples, which I did as well, because quite frankly I didn't have an easy way to automate the gathering of the data. But having seen the issues on this slide here, when I took my samples, I focused very heavily on this bottom level. I did take samples all the way up, but I took a lot of samples at the bottom end here because I really wanted to see what was going on at this bottom end of the waveform to see whether this was true. So this is the analysis that I did of the current draw graphed out, and what I did was I ran tests with each of the colors and then on white, and then I also produced a line which represented the sum of all the power draws across red, blue, green to see whether that was actually the same as the power draw for the white after I subtracted out the base current draw that the pixel has when it's not doing anything. And what you see is that it has that kink in the bottom as well. It kicks in at around about the 25-30 mark. The line basically drops away. You also see that the 12 volt regulated LEDs do a slightly better job of providing even power to all of the LEDs. You see a little bit of difference here with the 5 volt current draw. The reds, I should have got the colours right, but the red here seems to be drawing slightly more colour. There's always a slight gap between what I actually measured on white versus the sum of the red, green and blue, which is the upper line. The 12 volt regulator uses about 15% more current at 240% of the voltage, so it's 0.6 watts versus 0.25 watts. Now this was all done with a single pixel under test. In fact, if you look again at the pixel, if I can get that in there, this is a square node pixel that has been hacked. All of the materials been removed, and then wires have been added to allow me to take the sample. And I did a similar thing with the 12 volt pixel in order to take those samples. So obviously if you scale these values up, any errors that might be in this data obviously gets multiplied out. So be careful in doing that. So what about the actual brightness? Is the current draw, the fact that the current draw is somewhat linear and looked pretty linear to me across all but that bottom end, does that translate into actual brightness of the LED as viewed by the person who's looking at the LED? And so the way that I decided I would try and test that was I laid my hands on one of these things. It's a VEML 7700. It's a lux sensor, so hypothetically it's measuring the brightness. And so I set up a test rig with an Arduino that was driving an LED, and it would basically send the appropriate value, red, green, blue, and then white, and it would measure the lux value that it would see from that LED. I put them all into a dark box, covered it all up to make sure that there was no extraneous light, and then measured the response curve of the LED to see whether the actual brightness was similar. Now, one of the risks with any test like this is the responsiveness of the sensor compared to the human eye. The datasheet claims that it's extremely accurate. If anything, it suggests here that it's somewhat undersensitive to the green lights. The green's down here and oversensitive to the red. But I don't know, that didn't bear out in the results that I saw and the attempts that I had to try and reconcile it, and that's where I'm not sure how much you can make of these results, but I still do think that they're quite interesting to take a look at. So what do the results look like? So I ran 3 tests. I used a 5 volt LED, a 12 volt regulated, and I have a 12 volt module, which is the 3 LEDs with a single 2811 chip that's being driven. The chart at the top here, this flat section here, is just because basically it peaked out the sensor. You can't compare values across the graphs because they're not necessarily normalized across the graphs. The test wasn't set up that way. But within a chart, you can look at it and ask yourself, is that linear? Am I seeing a brightness curve that is linear? And the interesting thing is that, you know, it's clearly it clearly is linear within a colour, but there's clear differences in the perceived brightness across the various LEDs. It is impossible to say that that's the sensor. The sensor could just be significantly more sensitive to green LEDs than it is to red and blue. I suspect that that's the case because when and you'll see in a minute, when I try to use these results to then adjust the colours to match, I didn't end up with a set of results that necessarily made sense. But you do see the linear, but the other thing you do see is you still see the kink in the bottom. So the kink at the bottom end is real. It's there in the brightness as well as the current draw, as well as weirdness in the waveform that we see. And there is something that is worthwhile saying there. It could also be the Adafruit library that I was using to read the results back. So even if the sensor is perfect, if the Adafruit library is trying to compensate in some way for the LED performance, that could also be skewing the results somewhat. So I'm not sure that the green is as out of whack as this seems to suggest. So that's where I went in and tried to realign the colour curve. So hypothetically, because this performance is largely linear, in theory what you should be able to do is apply a dimming value to the green, and you'd have to make a slight dimming value to the blue to bring them all immediately into sync. And then if you turned everything onto white, hypothetically it would look like a better white. However, that's not what happened. So if I did that adjustment, I would leave the red at 255, I drop the green to 51 and the blue to 153, but it ends up really, really pink. What I did find, however, is that if I went to 255, 235, 255, I did get a white that didn't have any overabundance of green. So maybe there is a bit of excess green. The green LEDs are a little bit brighter, and that would suggest that a dimming curve that lowered the green slightly would help with the colour output and make it a little bit more even. But definitely it doesn't suggest that these values here can be taken at face value and just applied. So then, in order to salvage this analysis and end up with something that actually ended up a little bit more interesting, I did dive into, well, what the hell's happening at the bottom end of the brightness curve. And so if you zoom in on the brightness curve here, you can see that there is this, the curve is at one slope, and then it almost like it changes and basically halves, the color slope halves once you get below about 25. Significantly lower. So this is not such a big deal if you're using the full range of colors, but remember when we said if you were using a 10% brightness, then all of your values are going to be in this lower end. Also not such an issue because your curve is going to be largely flat. But if you're running at 20 or even 30% brightness, it does mean that your brightness curve, your power curve, etc., has got this skew in it. For if you're using a 30%, you're getting values between 0 and about 75, and for the top 50, the curve, the slope of the curve is 1, and then when at the bottom third, the slope of the color response changes, and so you're going to get a different color response at the bottom end. So it does make the case for you either want to run it at 10% or you want to run it a lot higher, or you just don't care about the bottom end and the fact that the the color response is not perfect. Oh. So that was my deep dive into pixel brightness and response. Before I move on to the second part where I look into pixel capabilities, any questions on that? How to set gamma? Well, there's two ways to set gamma. You can either set gamma in X lights by going to the model and going down to the dimming curve. And if you go into the dimming curve on the model, these are the gammas. So if you set the gamma here to 2.0, you can see you get that gamma curve. You can actually set it per color as well. So if you wanted to, you could say, actually, I just want a 2.0 gamma curve for green and 1 for red and blue, or that's a 20. That's not exactly what we wanted. So you can actually control it even at the individual channel level in X lights. On your controller, it tends to be a lot more limited. So if you go into your controller on your pixel settings, you will typically just have a gamma where you have a limited range of values that you can set. So you don't get as much flexibility, and you can only apply the gamma across all channels simultaneously. So yeah, you don't have as much flexibility.
Somebody asked, is the point of gamma correction just to adjust for variations in coloration when using lower light?
Yeah, that's exactly what it is, because things don't necessarily respond in a linear fashion. A gamma curve allows you to compensate for it. Typically, the color response curve is not a flat line. It has got a kink in it. It either kinks up or it kinks down, and applying a gamma allows you to drag the values closer to a straight line, so you're getting that straight line relationship between the value that you're sending and the color that you're seeing. Interestingly, in photography, you typically applying gamma the other way because it's an absorbent color. So rather than applying something that drags the brightness down, you're actually applying something that lifts the color for those middle colors, those middle ranges. So let's talk about pixel types and capabilities. And so, as hard as it is to believe, WS2811 12 volt regulated, resistive and 5 volt pixels aren't the only sorts of pixels that are out there. There's actually a huge variety of pixels out there, and I wanted to go through some of those different types. Not the form factors, there's obviously lots of form factors of pixels, but the actual the chips themselves and the capabilities of those chips and what they do, and go through some of those sorts of things. The vast majority of people run 2811 or a compatible version, and we'll talk about that. They either run bullets or square nodes or strip lights. But there are lots and lots of other capabilities. The thing I would caution before you go and buy any of these more esoteric types of pixels is check very carefully with your controller compatibility. If you're running something like an Advatec controller or a Falcon controller, you've probably got a fair range of pixel types that are supported, but some of the other controller types are much more limited, and some of them very limited in the controller or the pixel types that they support. And if you're going to buy anything that's weird or wonderful, you may want to get a sample before you commit heavily to those pixel types, or you might find yourself needing to go out and buy yourself another controller, or try to work with your controller vendor to get those pixels to work with your controller, which you may or may not be successful in doing. So just be really careful. And be very careful when a vendor says to you that, oh, this pixel's compatible with that. That may be true, but it also may not be true. It may be that it's very similar but not quite the same. I'm going to present a slide at the back end of the presentation that shows you all the pixel types which, as I understand it, are compatible with 2811s. But when you look at the individual data sheets, they're not identical. There are differences, and I could well see that there might be slight timing differences on controllers which would potentially make pixels which on one controller work fine as 2811s not work fine on another controller. So be really careful about that. Like I said, the variety here is quite staggering. The packaging of them, the chip capabilities, the protocols, the loads that you can drive are all quite different. The packaging itself is quite different. You'd all be familiar with your bullet pixels, which have a 2811 typically chip, or 2812 or 2815 or 18 chip actually in the pixel. You know, it's that little black square, generally multiple pin device. They do vary in terms of their capabilities. Some of them are able to drive more current than others. Some of them can control more than one LED. Most of them control just one, but there are packages out there that will control 3 or 4. You also get the ones where the microchip is actually embedded into the LED itself, and so you'll see packages like this 5050 LED package where there'll be a little black dot on one of the little markers in here, and that will be the actual microchip itself built into the actual LED package, rather than having to have a separately soldered on integrated circuit. Now, you'll typically only see these in, well, you'll mostly see these in strips. I won't say you won't see these in pixels. There are some types of pixels, he says, reaching for one. So there are these sorts of pixels. So there are these sorts of pixels here, which are actually, yeah, they look like a bullet pixel, but there's actually a 5050 LED in the end of it mounted on a PCB. But they're relatively uncommon. Most of you have seen these sorts of pixels. He says, not quite in shot. These sorts of pixels where there's actually a 4-pin LED that's actually soldered onto the circuit board. And most of your bullets and your square nodes are that sort of pixel. All right, the chip capabilities themselves are quite different as well. So there are chips out there that will drive 4 channels rather than just 3 channels. This is typically used for RGBW type pixels, but it doesn't have to be. There are people out there that sell pixels which, you know, use amber instead of white, particularly common in things like floodlights and the like, where amber is quite popular. The color depth also varies significantly. So something like, oh, I've got pixels everywhere here. So something like this thing here, which is a Minleon pixel, is a 16-bit pixel. It's a UCS 9803, and so rather than just being 255 channels per color, it's 255 values. It's actually 16 bits of color depth. So you get a lot greater depth of color. It's a little bit wasted with X-Lights, because X-Lights obviously only generates 8 bits of color depth. But a lot of these pixels also allow you to do things like map certain values to certain color values, and that allows you to build color curves actually within the pixels themselves. But other pixels have less, all right? So I've got a set of pixels here which only offer 5 bits of color depth. So it's a value of between 0 and 32 is all the pixel will accept. And they're LPD 8903s, I think they are, which only have 5 bits of color depth. But there's also 12 bits and 10 bits and 7 bits. It's all quite different. Obviously, this is a challenge for the controller, because the controller has to be aware of how to structure the data. You also can get chips which are able to deal with failure scenarios and continue to pass data in failure scenarios, and I'll show you some of those as well. And like I said, some of the chips have inbuilt brightness, gamma, and color mapping actually built into the pixel themselves. They typically require a very special set of data to be sent out by the controller to the pixels, but there are things like global brightness controls, but you can also have the controller send out basically a mapping table that says when you get this value, this is the actual 12-bit or 16-bit value that I would like you to display, allowing you to set color very, very precisely. That would matter much more significantly if you were trying to build, something like a video wall or something where the variations in the pixels would be a significant problem. In our sorts of shows, most of our controllers don't support this stuff, and even if they did, I doubt many people would bother with it. It's just a lot of hassle. The bypassing of a failed chip, this is generally only implemented on strip just because it requires an extra wire to run between each pixel. And this also gives us an opportunity to talk a little bit about how the pixels take the data. So here, this is a 5-volt pixel. You've got a ground line and a 5-volt line, and then you've got a data line. And the data line is sending all of the data to all of the pixels on the string. And the way it works is the first chip sees the data come in, and it takes the first 24 bits of data and uses it to light up these 3 LEDs. It then passes every piece of data that it receives after the first 24 bits down to the next chip in the chain, which it does exactly the same thing. It takes the first 24 bits of data and lights up its LEDs, and then passes the rest of the data on. How does it know when to stop passing the data on? Well, effectively what happens is the data signal goes low for a period of time. Typically with 2811 chips, it's about 50 microseconds. And at that point, this chip knows to stop passing the data on and to take the next piece of data as data for the first chip. And that's how the frames work here. But when you've got this bypassing a failed chip, you'll notice that the data that's coming in here is not just going into the DI on the first chip, but it's also going into the backup input on the second chip. Right? And when the data comes out of the first chip, it just doesn't go into the data input onto the second chip, but also goes into the backup input onto the third chip. And what happens is if this chip here is not seeing any data coming in on the data in chip, it knows to use the backup input. It will drop the first 24 bits because it knows that that wasn't for it, and it will take the next 24 bits to light its pixels up, and then it will pass the rest out the DO. So if there is some failure on this chip here, if this wire going to the DI is cut, or the wire going to the data output is cut, or the chip itself fails in some way, hypothetically the rest of the strip will continue to perform as previously did with this. Now this is a WS2818 configuration here. Now the reality is I've been running pixels for a long while, and I've seen a lot of failure scenarios. It is much more common for one of these color channels here to fail in some way than for a failure like this. And there are lots of ways in which this could fail and not fail over correctly. So I'm a little dubious that this is really that big of a selling point, but this is what it is sold as. Chip speed. So the speed of the chip is governed largely by its input protocol. The vast majority of pixels run using this 800 kilohertz SPI, which is a type of way in which microchips talk to one another protocol. It's a very simple protocol, and I'll cover it in a second. I'll use a slide from last year's presentation to talk about this, but this is a very simple protocol for transferring data between pixels, and they use this quiet time at the end between frames in order to reset and go back to the next frame. But this limits your frame time, right? And so if you look at last year's presentation, this slide was in last year's presentation. It's all based on the 2811 chip. it runs on an 800 kilohertz self-clocking signal, and so a high signal, well, a low signal has this rise where it goes up to 5 volts, it drops back down again, and the sample is taken basically a certain period of time after the start of this rise, and by that time the signal's low, and so it gets read as a 0. When a 1 is sent, it goes high at the same time, but it stays high longer, so that at the sample time the signal here is being read as a 1. And so this duration of this signal is fixed by this 800 kilohertz speed, which results in a theoretical frame rate where, and all the calculations here you can work through, but effectively if you're running 40 frames a second, right, then you've got 25,000 microseconds, which is 25 milliseconds. You have to take off 50 milliseconds because you need a reset time at the end of the frame in order for the next frame to happen. So if you take that amount of time and divide it by the 30 microseconds that it takes to send out a pixel is 33 bytes, right? So that takes 30 microseconds. You get this theoretical maximum of 831 pixels. So no one can run 40 frames per second for more than 431 pixels. Of course, in practice, no one actually runs anything this high because the controllers actually need time to prepare the data and transmit the data out, or to prepare the data for transmission out, and that takes a non-zero amount of time. And although the controllers do overlap a lot of that processing with the transmission time, it can't be zero. Right, so the more pixels that people are driving within a time period is just governed by how much of that processing time they have to hold aside in order to prepare the data to send it out to the pixel. So these are the theoretical maximums. In practice, this is the 831 is generally about 680, and I think the FPP-based controllers allow you to configure is at 1200 or maybe even 1400 pixels, but that's as far as they'll go at 20 frames a second. But that's not the only strategy. The other strategy that Pixels can use is clocks, and you will find some Pixels out there that have a fourth wire, and that fourth wire is used to send a clock signal to say, the data is ready, the data is ready, the data is ready every time that clock occurs. And that actually allows you to drive the signal to the pixel a lot faster. There are pixels out there which will allow you to drive clocks as high as 30,000 kilohertz, which is a pretty substantial increase in speed. I doubt anyone would run it that fast. You would potentially run into other reliability issues and capacitance issues and the like, but you can run pixels a lot faster if you use clocked pixels. Many of them, most of them will allow you to send it out at least 10 kilohertz, but it can go substantially higher in some scenarios. So if you really wanted to drive hypothetically more pixels and get yourself away from this 800 kilohertz limit, which is largely driving these limits, you could hypothetically move to something. Now you'd need a controller that was able to drive things this fast, etc., and I'm not even sure they exist, but that's it. From a load perspective, it's possible to not just drive LEDs from a PWM chip. You know, it is also possible to run much higher power things. So you may have seen pixel packages like, he says, grabbing his camera again and getting it into shot. So you might have seen pixel packages like this, which package multiple LEDs in, but still have a single chip in the back there. These things have extra transistors in place to enable the 2811 chip to drive more LEDs than just one. Very few 2811 chips or other chips would allow you to drive that many LEDs off a single 2811 chip. And so they'll often have a transistor or a FET or in some cases you can even drive AC signals using something like a triac, because the chips just can't sink that much current. They would burn out very, very quickly. And that allows you to do things like run floodlights and the like. So if anyone's bought any of those 10 watt or greater 2811 floodlights, those things would have a 2811 chip in them, but then they would also have probably a set of FETs attached to the outputs to drive the actual LEDs themselves. It could not be driven directly from the chip. And this is my final slide before I take questions. So this is some work that I've been doing. I've been working with Dave on the Falcon controller, and part of that process is looking at all the different types of pixels out there and trying to work out exactly how each pixel is derived, and this puts them into families. I don't warrant that this is 100% correct. Some of this has been tested. Some of it's based on lore from long past, where lore, as in LORE, not LOR, where people have historically grouped certain groups of pixels together as being signal compatible. But you can see that there is a fairly significant range of classes of pixels. The 2811 class has a large number of pixels in it, which are all very, very, very similar based on the data sheets and all look to be the same. But there are lots of others as well. The 2801s are very old school clocked pixels, largely replaced by 2811s these days. Very few people go with 2801s. The UCS 8903s and 8904s are 16 channel pixels, 16-bit pixels, 3 and 4 channels respectively. So if you want to run RGBW, what the 8904s, 8903s are RGBs. The TLS 3001s, these are 12-bit pixels. So they've got an extra 4 bits of color, gives you 4096 per channel rather than just 255 different values per channel. But then you get to the LPD 6803s, which have only got 5 bits per channel. And you've got various things. 4-channel, the APA 109s are all 4-channel pixels, and the ones with the triangles here are all clocked pixels. So there's quite a variety of pixels, and this is not extensive. There are other types as well that I haven't included on here, all of which have either more weird and more wonderful protocols, are much less supported. I think some of these you can probably get on the Avatec controllers. You might get 1 or 2 of them on the Falcons, but the rest you're probably not going to find on any of the controllers that we're likely to get.
Oh, thank you. So my question is, going back to when you had the 12 volt and 5 volt and you were testing the colors, was your results that 5 volt was less color loss, or is it the power? I mean, I wasn't quite...
You mean this one?
Yes, sir.
Look, you can't compare the values across these charts. They're not calibrated in a way that makes the values comparable. What this says to me is that they're all linear apart from the bottom end, and they're all fairly consistent in terms of how the brightness of the various colours have been received. I don't see anything here that says to me regulated or non-regulated is any better or different. I will tell you that I'm testing a single pixel here, right? So once you start to add in, I've got a long string of pixels. I will tell you that a regulated string of pixels will deliver a more consistent voltage to those pixels as you go down the string. And the reason for that is, and we covered this somewhat last year as we were talking through signaling, is the way in which the voltage divider works versus the regulator. The regulator takes an input voltage that has to be 5 volts, typically plus about 0.6 volts for the regulator, sometimes a little bit more. And on the output side of it, it gives you 5 volts. And it doesn't matter whether it's 6 volts or 12 volts, you still get 5 volts out the back end. But with resistive pixels, the way the voltage is dropped to 5 volts is using what's known as a voltage divider, which is effectively 2 resistors. And so as the input voltage drops, the output voltage from that voltage divider also drops in a proportional manner. So if you're getting 5 volts on the first pixel where the input voltage is 12 volts, right, then by the time you get to 6 volts, halfway down at the end of the string, that 6 volts is actually outputting a voltage divided output of 3 volts, which is driving your 2811 chip and driving your pixels. And you're not going to get the same performance.
Okay, and then over here it says that the brightness level has nothing to do with this output, correct?
The brightness, so within a chart, so as you look from 0 to 255, things are comparable. You can't look at this bottom chart and the middle chart and the top chart and compare them. They don't represent anything, because if that was true, this would say that the 5 volt brightness basically maxed out at only 180, right? Whereas these, it didn't max out at all. But that was just because I didn't calibrate the 5 volt test as well as I calibrated the two 12 volt ones. And these pixels are way brighter. These 12 volt modules are way brighter than the 12 volt regulated or the 5 volts, because there's actually 3 LEDs in it. But I had to structure the test such that the LEDs didn't send their lighters directly to the sensor, so that I didn't overwhelm the sensor, because I was more interested in the shape of this curve across the values than I was in the absolute brightness.